So we're starting with a performance engineering parable here. This is the repeated matrix vector multiply. So what we're doing is we're multiplying the vector D by the matrix C, and then we take that result and we multiply it by B to produce A. So there's kind of two ways that we'll consider to approach this kernel. The first is that we can multiply them all together in the same loop. And the second is we could do it separately. We could multiply C by D first and then take that result and multiply that by B like I narrated. So if we look at the two corresponding loop structures that result, on the left we have this triply nested loop that results from the three indices that we need to sum over in our expression. And on the right we have two doubly nested loops. If we look at the asymptotic complexity of these two algorithms, on the left we have an O of ijk algorithm if all the dimensions are the same size. That's an O of n cubed algorithm, whereas on the right our algorithm is O of n squared. And this is a factor of n speed up. Now, there's many optimizations that are equally applicable to both sides. You know, performance engineers could do something like parallelize or cache block or enroll, and they're kind of, they could apply to both of these equally, but it's difficult to beat that factor of n asymptotic speed up. So we choose the kernel on the right-hand side. This optimization is easy to spot by hand, but it's also automated in systems like the tensor contraction engine. So asymptotic speedups usually overshadow other concerns, and so oftentimes we perform these optimizations first, and then we do the constant factor stuff later. So we'll zoom in on our optimized, or our more optimal kernel, and we see it's two identical matrix vector multiplies. So we'll just look at one of them here. We could do this row major, multiplying the vector W by each row of B, taking dot products to produce A, or we could do this column major, scaling each column of B and adding the scaled columns to A. And these produce the same result mathematically, and they're both O of ij asymptotically, so they would both be good candidates for performance engineering. But this is not the case when the inputs are sparse. So what do I mean by sparse? A matrix is sparse when its entries are mostly 0. And this is actually quite common. It shows up in graph algorithms or scientific applications, sometimes showing up in neural nets. And it shouldn't be a surprise. Sparsity kind of represents connectivity. So if you think of this matrix as, say, a social network, then an element would be non-zero if our two corresponding smiley faces are friends. Now, no matter how popular you are, you can't really be friends with everybody, and so we would expect the number of non-zeros to grow slower than the full size of the dense representation. This is an asymptotic opportunity. We can skip multiplication by 0. We only need to multiply the non-zeros. And you know, in fact, it's common in practice for each row to have, say, a constant number of non-zeros. So this is a big improvement. Sometimes the full matrix isn't even representable. But this also poses new challenges because these sparse programs have different behavior than the dense ones. Going back to our example, in the dense case, it didn't matter row major or column major, but we'll take a look at what happens if we do a row major iteration on the sparse kernel. So here we have, we only need to multiply when the non-zeros are shared, but we need to iterate over both the row of B and the vector W to figure out which non-zeros are shared. And so this cost induces extra computation. Our row major algorithm is going to visit the entirety of B, even in cases in the third row here where the whole row is shared, or if none of the elements are shared, happening in this last row. The column major iteration is more efficient. So the reason we like column major better is that we can actually look at the vector W before we iterate over the column to figure out if it'll be 0 or not for the whole column. So as we iterate over this first column, we know W's non-zero for all of them, but we can skip that second column because we knew that W was 0. And so this algorithm only does the required iterations, so it's asymptotically the best we can do. You can compare that to our row major iteration that read the entirety of B. And this story doesn't just apply to loop reordering. It also applies to things that used to be asymptotically equivalent in the dense case, like loop fusion. And the sparse case also introduces new choices that we didn't consider entirely. Things like the format that we use to store the non-zeros, so which data structure stores their locations. You could use a hash table, you could use a sorted list. These have different asymptotic properties. There's questions about whether we should store it in row major or column major order. And I'll also remark that these different data structures have different capabilities. It's easier to randomly access into a hash table, and it's better to iterate over a sorted list. And finally, I'll say that the behavior of a sparse program depends on the input pattern. So, we see that in our last row of B here, none of the elements were shared, but that's specific to this particular pattern. It didn't have to be the case. So with so many options for how we might implement these kernels, it's too difficult to do by hand, which has led to the introduction of sparse tensor compilers. So here we have our domain expert. She's a scientist. She's got some computations that she'd like to execute and some input data to crunch. And so she passes both of them to the tensor framework. But there's a ton of options, like I said. So what we do is we'll summarize the options into a high-level, what we call a schedule, which we would usually employ a performance engineer to produce. So the performance engineer would look at the kernel and produce a really good schedule for it. Now, having a human in the loop means that the system can be more difficult to use. It relies on somebody who's an expert in the compiler. So ideally, we'd be able to introduce an autoscheduler to produce these kinds of schedules automatically. The autoscheduler is also useful if we wanted to integrate the system inside of like a higher level system like NumPy. Now that there's no human in the loop, it can be a subcomponent. We typically measure the runtime of our kernel from the point at which the input program was received. So here we see the input data, we put it into the tensor framework, and we already knew the schedule. But recall that the runtime of these kernels is pattern dependent. So the best schedule to use might depend on the input. In that case, there have been techniques that use the input pattern in the autoscheduler. But if we're going to do that, we need to start measuring the runtime at the point at which we read the input. And so the autoscheduler is now part of the runtime, which could slow things down. So in this work, we focus on the kinds of optimizations that we can do without looking at the data. And so this means that we no longer need to have our autoscheduler as part of the runtime. And the way that we'll do this is we'll model our program runtime symbolically. So if you think of these sparse loops, they're functioning as filters. And filters are kind of just loops with if conditions inside of them. So here we have our little example kernel with a couple of loops and an if. And what we'll do is we'll model the runtime as proportional to the set of tasks that the program executes. So recall, usually when we try to asymptotically analyze a program like this, we might say that its runtime is O of ij, but that's not precise enough in the sparse case. So if we wanted to precisely characterize the runtime of this kernel, we'd say that this foo is printed once for every element in I. Bar would be printed once for every element in I where C is true, and then quux would be printed once for every I and j where C is true. And so we can combine all of these into one big runtime, and we get a much more precise representation of the work that this kernel does. And throughout the rest of the talk, we'll use kind of a simplified version of this. So here we can use this to explain the example that I showed at the beginning of the talk. Our column major traversal iterates over all ij, where w and b are non-zero. And our row major traversal iterates over all ij, where w or b are non-zero. And so because the set of iterations that the row major program iterates over contains the set of iterations that the column major program does, we know that we should choose the column major one. So we can integrate this observation into an autoscheduler. We start with our tensor expression. We enumerate a couple of schedules that we'd like to choose between. And then we need to do two things. The first thing we need to do is generate our asymptotic cost model. And then we need to be able to compare our models to each other. So in the case of loop depth, we generate our model by counting the number of loops. And then we filter by using less than. But if we're going to use our iteration sets, or our sets of tasks, we'd generate those by compiling the schedule. And then we can compare them to each other using set containment. Now, the database literature has several algorithms that allow us to compare sets syntactically. And so the result of this filtering can reduce the size of the frontier that we consider by factors of over 100, even after filtering for the loop depth. And this explains some performance engineering choices that we see made in practice. You can consider the sample dense-dense matrix multiply. What we're doing is multiplying the matrix C by D, where both C and D are dense, and then we'll sample the output with the sparse matrix B. So here we compute each dot product between rows of C and columns of D, and then we sample it with B. And executing this separately, as I've shown, we need to do iterations over all I, j, and k. But if we fuse it, we can predicate the set of iterations based on only the elements or only the dot products that are requested by B. So here we're able to skip some of the dot products. And we see that our fused iteration set is contained in the unfused one. So finally, one last performance parable. There's 3 approaches to sparse matrix-matrix multiply that are typically considered in literature. So here we're just doing a regular matmul where B and C are both sparse. There's the inner products, Gustafson's, and outer products algorithms, and they're all loosely characterized by their loop ordering. So the inner products algorithm is characterized by the reduction loop where B and C are joined as being the innermost loop, whereas Gustafson's and outer products are the middle and outermost loop. So this K is the reduction loop here. And if we produce our somewhat abbreviated asymptotic expressions for the set of iterations that all these 3 algorithms do, we see why practitioners prefer Gustafson's and outer products over the inner products approach, because the inner products will filter for every combination of J and I. And this kind of asymptotic analysis, even though these 2 programs have the same loop depth, we see in practice that the sparsity, considering sparse asymptotes matters quite a bit. What we're looking at here is the runtime of both inner products and Gustafson's algorithm. And on the x-axis, we have the sparsity of the matrices. So we're keeping the size of the matrices the same, but as we go from left to right, the matrices are getting sparser and the speed up is increasing up to 1300x. And we see this across several different kernels. So our cost model is able to identify these asymptotically unwise options over a great variety of kernels. So in conclusion, the previous notations that we used were not precise enough to characterize sparse programs, and our model is able to accurately explain practitioner choices. We've shown that it's possible to implement this analysis as part of an autoscheduler. And I guess finally I'll say that we really believe that this is the auto-tuning or auto-scheduling is really the last hurdle that we need to make sparse tensor compilers accessible to the mainstream. So with that, I will conclude my talk. I have a couple of links here if you'd like to check out the paper. And I'll do a final remark and say that this code base was written in Julia. It was a joy to use. And we used a symbolic manipulation library called Symbolic Utils that made it a lot of fun to write. So that's it.
Great talk, thank you. I'm more familiar with the Halide cost model. They basically just, they model a lot of program features and they use those program features fitting into a cost model and trying to use the cost model prediction, the actual running time of the program. So I'm pretty interested in your thoughts about why asymptotic running time is so useful in a sparse tensor compiler comparing to like a compiler in Halide. I mean, Halide definitely can try using asymptotic running time, but they chose over like actual running time. So I would like to hear your thoughts about it.
Yeah, using an asymptotic cost model is it can be useful because it allows us to do certain analysis without seeing the input patterns. So that's the first thing I'll say. But this cost model is also it can be adapted if you'd like to produce features that actually characterize the number of inputs of an actual program. If you wanted to use these set notations, you could calculate the sizes of the sets once you see the patterns as well. So if you wanted to use it that way, you could. So yeah, does that help?
Yeah, thank you.
So I have 2 questions. My first question is in the first slides you showed that you separate a complex tensor expression into 2 expressions so that the time complexity is reduced. Do you consider fusion after you separate those kernels, like a partial fusion opportunity I'm talking about? And then my second question is, can you comment on the complexity of this, your algorithm? Like you have many schedules in your algorithm and you do loop permutations and then you filter it out, like the complexity of the algorithm, what does it depend on? Does it depend on the indexes? And can you comment on that?
Yeah, so to answer the first question, I'm not entirely sure whether it's possible to fuse these two because there's a dependence between them. So
sorry, I'm not specifically talking about this kernel, but there may be instances where
I see, where you have two similar loops.
Yep.
So I don't believe we consider that kind of an optimization if it doesn't change the asymptotic complexity. So the way that we enumerate our equivalent programs is we start with the fused kernel and then we evaluate all the possible ways to split it up. So we don't do a separate fusion step later. You would discover that by not separating a kernel, I think might be the way to say it. And then to answer the second question, this is what I've described here is a form of program synthesis by enumerative search over syntactically equivalent programs. So there are an exponential number of programs to consider, and the algorithms that I mentioned to do the comparison between these sets take at least exponential time. Syntactic set containment is a complicated question to answer, but because we're not doing this at runtime. We found that we were able to run a lot of these algorithms anyways. I think the other thing I'll say is I actually have a backup slide for that, which is that the sizes of these kernels are usually small. So if we look at like the set of all kernels that were submitted to the Taco web tool over the course of its lifetime, we see that like there's a median of 6 tensors in each expression and a median of like 3 indices. So these kernels that people are interested in are usually small, and what we really would like is a way to enumerate asymptotically okay starting points for further optimization.
Thanks.
So as you generate these sparse kernels, do you generate vectorized load, store, and compute as part of the schedule? Is it part of your search space? First question. Second question is, do you consider the target ISA as you search for these schedules? Because for the dense case, that's the dominating factor for why a dense kernel will be faster than another one.
Yeah, so I think the answer to both questions is no. We're not considering constant factor optimizations like loop unrolling and stuff like that. The speedups that we've shown are from simply loop reordering and from loop fusion optimizations like that. And I guess to answer the second question, we don't consider the target because the number of iterations that the program executes is target independent.
Well, thank you. So it's purely just scalar code, right?
Yes, we're doing serial code.
Scalar.
Oh yes, scalar code.
Okay.
Yes.
Yeah. Thank you.
Okay. That
Thank you all.
Is time.